at IISc. Before we go ahead with the program, there's a small announcement about a change in the schedule today. So the third talk today, which was supposed to be given by Shantala MN, is going to be changed, and we will instead have Jayakumar Subramanian from Adobe Bangalore speaking on the third slot, in the third slot. Okay. So we'll proceed. We are very happy today to welcome Professor Nan Jiang from the University of Michigan. So he's an assistant professor. Yeah.
Sorry, I'm currently in UIUC.
Oh,
Michigan is where I got my PhD.
Very sorry. Yeah, pardon me for that. So he's an assistant professor of computer science at UIUC. He got his PhD from the University of Michigan, and after that, he spent some time as a postdoc at Microsoft Research in New York City. So he's made contributions to reinforcement learning theory, specifically sample complexity exploration, and many of the core topics in reinforcement learning. He's been recognized for his work through many awards, including the NSF Career Award and a bunch of Best Paper Awards. And he's especially known, at least I know a lot about this reinforcement learning textbook or monograph that he's been writing in collaboration with, I think, Sham Kakade and others. So I urge you to go and look it up to get some serious pointers on reinforcement learning theory. So with this, I'll hand it over to him to tell us about the theoretical foundations of reinforcement learning and how to rethink them. Over to you.
Thank you very much. It's my great pleasure to give a talk here today. And it's I couldn't travel there, but please bear with me. And if you can't hear clearly or if you have questions, feel free to ask and let me know. Okay, so today I'm going to tell you some results from my group in recent years that I'm particularly excited about. And I want to start by sharing some high-level perspectives on the current status of RL and raise some questions that I feel are very important and motivate my research. So RL has seen many impressive successes, right? AlphaGo beats human Go champions, RL agent deployed in popular games, and we even hear about RL-based control infusion reactions. Now, if you look closer into these cases, the commonality is that they all happen in simulators, where we have unlimited amount of training data and can learn by trial and error without ever worrying about taking suboptimal or even risky actions. On the other hand, many important potential real-world applications for RL do not come with high-fidelity simulators, especially when humans are part of the environment, such as in medical scenarios and online recommendation systems. So even in robotics, we often cannot just fully trust the imperfect simulators and may need to close the sim-to-real gap using some real-world data. So in these scenarios, the majority of current RL algorithms that rely on the convenience of simulators are simply not directly applicable. So to tackle this challenge, the community has reached the consensus that offline RL, where we train agents solely based on pre-collected historical data, is an important paradigm to bring RL to real life. Now, it's been a few years and thousands of papers are published on this topic, but where are the real applications? Right? So why are we not seeing offline RL deployed already everywhere? And what are some of the missing pieces? Okay, so that's my first question. My second question is about the theory versus practice gap, right? So if you have some exposure to RL theory prior to 2015, you may have the impression that it's all about proving error bounds in MPPs with finite and small number of states, right? And in contrast, the deep RL community, which has grown enormously over the past, say, 10 years, is all about dealing with high-dimensional state spaces and developing practical algorithms with neural nets. Right. So while recent RL theory has also seen much development and we can deal with functional approximation, the mathematical foundation that fuels the development of deep RL today still arguably comes from early 2000s or even before that, right? So now we know that the impact of the theory can be indirect, can be delayed, But still, the question is, can theory have a more direct role in modern RL practice? Okay, so my last question is about the theoretical foundation, right? So as I alluded to earlier, while everyone wanted to address complex environments, to build a theoretical foundation, we often need to first simplify the problem. And so in RL, the way we did it traditionally was to move away from the complex environments and study the toy problems with finite and small state spaces, right? So this well-known so-called tabular RL setting. We developed a mature understanding there and then extend our algorithms and analysis back to the complex environments. The question is that the only way to build a theoretical foundation for RL, right? Or are there other formulations that will give fundamental insights that have just eluded us for years? So as a little spoiler, one concrete approach you can think of is not to simplify the environment, but to simplify our hypothesis class, right? So, and this is exactly what we did in learning theory, right? So instead of having neural nets, how about we go back and to discrete hypotheses classes, or actually just think about the problem of comparing two hypotheses. While this is completely trivial in supervised learning, a version of this problem in RL had been open for more than 20 years, which is what I will talk about shortly. Okay, so in today's talk, I'll tell you something that touches on all these three questions, and hopefully convince you that by rethinking the theoretical foundations of RL, we can provide unique perspectives and solutions to practically relevant problems that are crucial to bring RL to real life. Now, let me start with one of the questions I asked earlier, right? Why are we not seeing offline RL already deployed everywhere? Okay, so to answer the question, we can first look at the most mature machine learning paradigm, right? So which is supervised learning, right? And see what lessons we can learn from there. And speaking of supervised learning, I think many of us will immediately jump to, deep learning versus kernel methods, boosting, etc., all these training algorithms. But I would argue that the massive real-world success of supervised learning is due to something much more fundamental that we often take for granted and ignore, right? And that is, when someone gives you a supervised learning data set, what is the first thing you do? Well, it's not running your favorite training algorithm. ML 101 tells you that the first thing you do is to split the data into training, validation, test, right? And you can try many different algorithms on the training set, but eventually you rely on validation to make sure that you select the best performing one out of them, right? And to me, this is the real backbone that underlies the success of every supervised learning application. So in offline RL, we can do the same, right? We can split the data, and the question is, how can we compare different training algorithms? Right, what I'm going to show you in the next few slides is that there's nothing remotely close to the reliability of holdout validation in supervised learning, and this is where theory can actually make a big difference. So recall that the final output in RL is a policy. So we need to compare the performance of different policies. And since these policies would generally want to take actions different from those taken during data collection, we're in this so-called off-policy evaluation setting. Okay, so let's briefly delve into this problem and see how it's typically approached, which will allow us to quickly go over the basics of RL and make sure that everyone is on the same page. Okay, so in RL, we think about a sequential decision making in a dynamical environment, right? So upon observing state ST, you take action AT, obtain immediate reward RT, and then transition to a random next state ST plus one. So given a policy pi that maps states to distribution reactions, we use jpi to denote the discounted expected return of taking actions according to pi from some starting state of interest. So the goal of policy evaluation is to estimate the scalar for a given policy, right? And policy optimization, which is the problem we care about in training, is often to find a policy that maximizes such a return. Now, to estimate this return, a typical approach is to estimate the value function, right? So in this case, for example, a Q function as an intermediate quantity. Now, this Q function, as probably everyone here knows, is the expected return when you start from a particular state action pair. And once you get this function, you can simply plug the initial state into this function to get a good estimation of jpi. And QPy satisfies the famous Bellman equations and can be recovered if we can enforce such equations for every state action pair. Of course, look, in any problems, the number of states is likely enormous and making this approach impractical. So instead, what we do often is to write down a function f parameterized by some theta, and we find the parameter theta such that f theta is a good approximation of q pi. And to achieve this, the fitted Q evaluation algorithm, or FQE, solves a sequence of least square regression problem iteratively, right? Where the regression target depends on the learned predictor from the last iteration, right? And here the expectation is over whatever data we have, collected, and in the form of transition tuples, and they are often extracted from trajectory data, in this manner. So this procedure mimics the well-known value iteration algorithm for dynamic programming and extends it to the learning setting, and can be viewed as the batch version of many algorithms whose I suppose like the audience here is very familiar with, like uh, 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 TD and all its variants. Right? So now if we take this algorithm and if we simply change the action selection from pi to a greedy action, max over a prime, we recovered the well-known fitted Q iteration algorithm, or FQI, which approximates the optimal Q function Q star to further induce a near optimal policy. So for the purpose of if you implement this algorithm in a more online stochastic manner, you essentially recover an algorithm very similar to DQN, right? If you're using neural nets. So for the purpose of this talk, you can think of we're going to treat FQI as a representative training algorithm, at least for the first part of the talk. We're going to treat FQI as a representative training algorithm. You get a policy pi out of it, and then you plug the policy into FQE to do evaluation, right? So, and this is sort of like, a concrete example of a offline RL pipeline that we talked about earlier. Okay, so now at this point, I hope that you can see the absurdity of this training validation paradigm, right? So when we do validation, a main purpose is often to tune the hyperparameters of training, right? And this includes the neural architecture, which defines the function class we use in regression. So what this framework tells you to do is that to do such tuning for training, you need to come up with an algorithm for validation whose structure is almost identical to the training algorithm. So if FQE tunes training, then who tunes FQE's own hyperparameters, right? So this is actually an elephant in the room that surprisingly few people are talking about. And my own opinion, my own belief is that the lack of reliable validation methods that are hyperparameter free themselves is actually the major difficulty to obstacle to deploying RL in real life applications. Okay, and so basically like you have a chicken and egg problem here. Okay, so now the question is, are there alternative validation methods that are indeed hyperparameter free themselves, right? So it turns out that the answer is yes. There's a family of methods with a very long history of being studied called importance sampling. Okay, so and it has many advantages, right? So the basic idea, and recall that basically the key problem here is that the data collection policy may disagree with the candidate policy we want to evaluate, right? So first of all, importance sampling makes a requirement that says, okay, data policy cannot be deterministic. It must be stochastic. You need to choose actions randomly. That's okay. Okay. Now, roughly speaking, what the importance sampling does is that among all the randomized action choices, you only look at those data points where the random action choice happens to match what the target or candidate policy wants to take, right? So therefore, you can get an unbiased estimation at the cost of reduced sample size. While this works very well for contextual bandits, and which can be viewed as RL with a horizon of 1, right? And has actually seen industry deployment, but it actually has a very serious problem when we consider the multi-step decision-making setting, right? First of all, in the full MDP setting, importance sampling requires full trajectory data, and that's fine. What's really problematic is that it will essentially throw away any trajectory where there's even a single action mismatch, right? So the probability that you can keep a trajectory actually shrinks exponentially with the trajectory length, or what we call the horizon. Okay. Now, some of you may know that we can use the so-called control variates to reduce the variance of importance sampling, and also known as doubly robust estimators. So it turns out that it was quite tricky to do it for RL for MDPs, but we figured it out in 2016. Well, guess what? Like even with perfect control variates, the exponential variance wouldn't go away if your environment is stochastic. Okay, so evaluating policies in a hyperparameter-free manner seems a dead end to hold-out validation, right? But turns out that that's not the end of the story. So recall that our training algorithms in RL do not simply just compute a policy, right? They often produce value functions as intermediate objects, right? So when we are choosing between different algorithms, maybe instead of directly comparing the policies, we can actually compare their value functions as a proxy, as a surrogate, right? So as we'll see next, the value functions themselves contain richer information and structures. So giving some hope that we can maybe choose between them in a more effective manner. Okay, so here is the reformulated problem. You run your different training algorithms, you get candidate value functions F1, F2, and etc. We have a holdout validation data set for as usual. And the task here is that let's make things simpler. If one of these functions is Q star, we would like to find it out, right? And to eliminate these degenerate algorithms or solutions that we know are not scalable or have crucial caveats, we're going to require that the sample size we use is small in the sense that it should have no exponential dependence on the horizon or any dependence on the size of the state space, right? So furthermore, we're not going to allow any further function approximation because any further function approximation is going to require additional hyperparameters, which goes back to the chicken and egg problem. And in fact, let's even further simplify the problem, right? So let's say we only have two functions, f1, f2. One of them is exactly Q star. You don't know which, but you have some nice holdout data and you want to find it out. And guess what? This is the question we had no idea how to do for like 20 plus years. So, and when I say 20 plus years, what I mean is that someone has exactly thought about this problem, not exactly in the context of selection, but a very closely related problem, in around 1995. Okay, so in this seminal paper by Lehman Baird in 1995, he didn't think about holdout validation because offline RL wasn't a thing at the time, but instead he looked at this problem through the lens of training. Okay, and we'll see that this training perspective will be very crucial to the resolution we're going to provide. And it also connects this problem to some of the very core algorithmic challenges in modern deep RL. So Lehman Bair's question was very simple, right? So can we design a loss function L such that this loss function is something you can estimate from data. And if you want to do value function estimation, you just minimize this loss function over a function class, and that's it, right? And if we can get a positive answer to this question, it will also immediately solve our problem of value function selection, right? Because we can simply let the function class to be the set of candidate functions we want to compare, right? Because after all, validation is just yet another training process on a finite and very small hypotheses class, right? Those candidate policies generated by different training algorithms. So for some who didn't read into RL theory very deeply, like your first question might be, wait a second, doesn't current RL algorithms already do this? Well, after all, this familiar paradigm is how most of the standard machine learning works, right? Especially in supervised learning, that you just have an optimization problem. You write down a loss function, estimate the loss from data, and minimize the loss the hell out of it, right? Well, guess what? We know that most RL algorithms actually don't work in this way, right? So especially like TD algorithm in the TD family, including Q-learning and their batch variants like FQI, they actually solve a sequence of regression problems iteratively. So it's optimization at a lower level, but iterative at a higher level, right? So all of them are essentially still dynamic programming algorithms. And this iterative nature is at least partially responsible for various training instabilities that we see in DeepRL, right? Such as catastrophic performance drop or bipolar performance across different rounds. And in theory, it can be shown that all these iterative TD algorithms diverge even with infinite amount of data and one-dimensional linear function class, right? Where the true value function is exactly linear. Even in that case, these algorithms can diverge. Okay, and to avoid such pathology, theoretical analysis, especially modern analysis in RL, often introduce the so-called Bellman completeness assumption, right? That the function class, sorry, that the function class is closed under the Bellman operator. And this is assumption because in general, the Bellman operator can just totally take you out of the function class, right? And you know, the other thing is that maybe this assumption makes some sense for training when you have a very rich and continuous function class, but it really doesn't make sense when we're in the validation setting where our function class is really just a handful of hypotheses. Okay, so long story short, you know, it would be really ideal if we could replace all the iterative algorithms in RL with simple optimization-based algorithms that has a consistent simple loss function. Right? It's kind of like a dream. And why is it so hard? So let's come back a little bit, from this little detour and see what Lehman Bear did. So his reasoning is the following. We know that Q star satisfies the Bellman equation. So why don't we just take the difference between these two sides of the equation and make that a loss, right? Now, this difference, which we often call Bellman error or Bellman residual, it is a function on its own. So it's not a loss function because loss must be a scalar. So let's just take the difference, take a square, and then take expectation over whatever data we have, right? So this is perfect, right? Well, unfortunately, when we expand the Bellman operator, we see that there is a conditional expectation inside the square, right? And this makes the loss function not estimatable from data. And in fact, the most naive estimation method you would come up with, which is the so-called one sample estimator, is known to be positively biased and positively biased. And debiasing it requires either a simulator, which we don't have in the offline RL setting, or it needs a additional helper function class to satisfy essentially a version of this so-called Bellman completeness assumption, which again run into the chicken and egg problem if our goal is to do holdout validation. Okay, so having seen the difficulty of this problem from the lens of training, I'm going to tell you how we solve the problem, okay? Which is to remind everyone, the simplest version of the problem is that we have two candidate functions, and uh, we want to, and one of them is Q star. We want to select between them. And to understand our solution, we'll need an old result from training by Jeff Gordon in 1995. So recall that iterative RL algorithms, generally diverge even with a realizable linear class, right? If with a linear function approximation. Well, if linear doesn't work, maybe something simpler can actually work, right? So it turns out the answer is yes. If you use even simpler function approximation scheme, which is essentially piecewise constant function classes, this corresponds to the well-known state abstraction or state aggregation, right? And in this case, things actually converge, okay? Even when you only have the so-called realizability assumption, that is, you only require Q star to be expressible by this function class. Now, this is for training, but we can also translate this result and use it in validation, right? So essentially, if someone gives you this nice piecewise constant function class, which we will call G in the context of validation, then problem solved, okay? So I have many, many different ways of using this G to select the right Q star out of the candidates. And I will talk about some of the examples later, okay? So, but to be clear, what's the criteria? What's the requirement we need on G, right? So it needs to satisfy three criteria. One is piecewise constant, okay? Two, it can express Q star or approximately express Q star. And three, it has small number of partitions, right? Because the number of partitions determines the statistical capacity of the function class. Okay, once this G is given, there are many ways we can use G. For example, minimize the so-called projected Bellman error. Calculate the projected Bellman error onto this G class of F1 and F2 and choose the one that had a smaller loss. And now, given this, of course, the next question is who gives you this G, right? So if we need G as an input, it's just yet another chicken and egg problem. So the key part of the method I'm going to tell you about is to show how can we create this G class, this magical G class, out of nothing, okay, without making any further assumptions. Okay, so as a first step, we first need to verify that this nice and magical G always exists, right, for an arbitrary MDP. Well, the good news is that it always exists. So to show existence, we can just conceptually assume that we know everything about the MDP. And if we construct this G, then we're good, right? Now, it's actually very simple. So if we know everything about the NDP, we can just take its true Q star function, discretize its output so that it takes finitely many possible values, and then partition the state action space accordingly. Okay, so in this case, and in this case, note that even if so here we're completely ignoring the topology of the input state action space, right? So maybe your state space is represented by real vectors, and maybe you have two states whose vector representation is close to each other. And naturally, you would think of in terms of non-parametrics and so on. I would say, oh, these two states are close, so their values should be close and so on. No, I'm not using any of that. Okay, for example, on this cartoon illustration, we have these little pieces that are very far away on the x-axis, but as long as their output is the same, we're going to call them the same piece, right? And in this case, and a direct consequence is that maybe your Q star is a totally crazy, non-smooth, crazily goes up and down, like jitters very, very badly. It doesn't matter. We always have a well-controlled number of pieces, right? And what's the pieces? What's the number of pieces? It's 1/epsilon, right? Where epsilon is the discretization and resolution that you use in the discretization step. Okay, so this is nice, but as you can see, I'm still using a chicken and egg reasoning over here, right? Because the whole point of having G is to help identify Q star from candidate functions. But what I'm saying here is that to construct G, I need to know Q star. Okay, now don't worry, we're only one step away from the final solution. Okay, so to solve the chicken and egg problem, so let's come back to our simplified version of the problem, right? So we have two functions. One of them is Q star. We don't know which. And the way we're going to solve it is that we're going to construct this magical G, that's piecewise constant, small number of pieces, and can express Q star. How do we do it? Well, very simple. We just repeat the procedure that we did in the last slide, but for both functions simultaneously. Okay, you discretize both functions' output, and then discretize the state action space according to the output of F1 and F2. And you call any two state action pairs aggregated when both F1 and F2 stay constant across these state action pairs, right? And in this way, you get a piecewise constant function class that satisfies all the criteria, but only with a size of 1/epsilon squared, right? It's not as good as the ideal case of 1/epsilon, but it's not too bad at all, given that we don't really have any polynomial solution to this problem. Okay, so this solved the case of two functions, but if you naively extend this to multiple functions, the size of the resulting G class would grow exponentially with the number of candidate functions, right? Which we don't want. So to solve this problem, our solution is to perform the above procedure across all pairs of functions, like running a kind of tournament. And then our theory shows that the algorithm, this algorithm, which we call the batch value function tournament, by doing this pairwise comparison, can actually efficiently compares a very large number of candidate functions, and the sample complexity is polynomial in the horizon in 1 over epsilon in the log number of candidates. So you can actually consider arbitrary pretty much any number of candidate functions you'd like, and a C parameter that determines how exploratory the data set is. And the one caveat of this work is that the data coverage assumption we make here is pretty strong, and I'm not going to discuss here. I'm happy to discuss later, but the data coverage part is what we're going to focus on in the next second half of the talk. Okay, so and moreover, the computation needed here is fully closed form. There's no optimization, nothing. It's like very simple closed form solution. So when you really have a small number of candidate functions you want to select from, we can actually just implement it, and we actually did. And we actually tested this in deep power benchmarks, and BDFT actually beats all kinds of heuristics that people have considered by a large margin. We also implemented FQE and cheated by using a very a hand-picked architecture that performs well in training. And guess what? Eventually FQE catches up with the performance of BFT, but that's when the data set you use for validation is as large as the training set, right? At a million level for these pixel-based game playing domains. And in contrast, BDFT, which is the red curve over here, I think, yeah, over here, it actually has way better sample complexity and performs very robustly, even with a relatively small amount of data. Okay, so to summarize the first part of the talk, I introduced BDFT, which is a hyperparameter-free solution to value function selection. Now, this by no means solves total validation, and there are many important open problems that remain. For example, as I briefly mentioned, DFT requires relatively strong data coverage assumptions in theory, and which we'll touch on related questions in the second half of the talk. And also, its behavior is very different from traditional policy evaluation methods. So I think there are opportunities to combine their strengths and create a toolkit that take the best of both worlds and make it effective for real-world users. Okay, so this is the first half of the talk. And in the rest of the talk, I'll switch gears a little bit and talk about training algorithms in offline RL. Okay, so it turns out that the modern understanding of RL algorithms is largely determined by two key pillars. One of them is function approximation assumptions, which we touched on briefly earlier, right? So this notion of Bellman completeness and so on. The other important aspect, which we have omitted so far, is to appreciate the challenge due to different policies inducing different state distributions, right? And this will be our focus next. And this line of work has led to an ISML paper award, outstanding paper runner-up in 2022. Okay, so let's first look at the classical algorithms and understand when they work, when they fail, right? And if you look at the analysis of fitted Q iteration, you always find this kind of condition that says this kind of condition as we listed here, where d pi is the state action distribution induced by policy pi, and we're essentially require the data distribution, the offline data distribution, to provide coverage over all possible policies, right? And under this assumption, which nowadays we call all policy coverage, and the Bellman completeness assumption for the function class, we're guaranteed to learn near optimal policy. Well, the problem is real-world data often lacks exploration. So, for example, in network management, data is often collected by a heuristic control rule that does not explore all actions and states. And in such cases, the concern is that data may not contain all possible bad behaviors. right? And as another example, let's say we're considering self-driving, we can collect a large amount of data, but most of the data would correspond to safe driving behaviors, right? And if a dangerous behavior is never presented in the data, how can the algorithm know that it's dangerous in the first place, right? So in fact, if you run these traditional classical algorithms, they can totally overestimate the performance of a bad policy that you don't see in the data, which leads to degenerate performance, if not catastrophic consequences. Okay, so so really what we want, right? What's the ideal situation here, right? So really what we want is to remove this data coverage assumption and allow for an arbitrary data distribution, right? So in this case, there will be policies that are not covered by data and will have no clues about what they're going to do, how they perform, right? But maybe we can still hope to compete with the best covered policy, right? And if we can do this, then we can still hope to learn very good policy as long as one single good policy is covered on data. So now if you think about this problem, the key is that we want our learned policy to stay within the data distribution, right? Not leave the data distribution. And this is exactly opposite to online RL, where the goal is to explore, is to leave the distribution, right? And in online RL, a very well-known principle is called optimism in face of uncertainty, right? Whenever we estimate the policy's performance, uh, we're gonna we're gonna imagine its best case scenarios, and by analogy, we should exercise pessimism and imagine the worst case scenario for offline RL. Okay, so more concretely, consider the policy optimization framework where we're trying to take the best policy out of a class of policies, big pi. So of course, the true performance of JPi is unknown, and we have to estimate it from data. And pessimism requires that the estimation, j hat pi, that we use in the algorithm to be a lower bound of the true performance j pi for all policies, including those that are not covered on data. And furthermore, to prevent, if this is only as the requirement, I can just, predict negative infinity for everyone, right? Clearly, that's not useful. So to be really, for this estimation to be useful, you also need to be tight in the sense that for all the covered policies, the estimation should be approximately correct. Okay, so whenever these two criteria are satisfied, we can achieve our goal of competing with the best policy. Sorry, with the best covered policy. Now, this by no means is a new idea, and we can find its root in robust optimization. Recently, we also discovered some very interesting connection between algorithms used in offline RL and that has direct application in robust MDPs, which I can talk later offline. So, um, but the new problem here in offline RL is how to instantiate it in the learning setting with function approximation. Okay, so prior to our works, pessimistic algorithms for tabular and the so-called linear MDP setting have been figured out. They use so-called pointwise pessimism, and I'm not going into details here, but the main idea is that you construct Q hat that is a pointwise lower bound of the true Q. Okay, and this approach has a number of limitations. First, the Q hat can correspond to impossible scenarios and leads to overly conservative estimates, right? So as an example, consider this problem where you have two doors and a prize is hidden behind one of the doors. You can only make a guess, right? And pointwise pessimism, look at each door separately and say, okay, in the worst case, is there a prize behind the door? Well, in the worst case, if for a fixed door, there's nothing behind it. So it just concludes that there's nothing that you can get in this game, okay? And of course, that's not true because, and there's a very simple policy that is guaranteed to get the price 50% of the time, which is to do randomization, right? So, and this is the case even if the true location of the price is chosen adversarially. So another limitation is that to obtain a pointwise uncertainty quantification, we need to introduce very strong assumptions on function approximation and expressivity, right? So recall that we already need this Bellman completeness type of assumptions, right? For most our algorithms. Well, it turns out that if you only have that, that's not enough to do pointwise pessimism. Because to do pointwise pessimism, not only the functions inside the function class needs to map back to the function class after the Bellman operator, even functions outside the function class needs to go to the function class, needs to go in the function class after one Bellman operator. Okay? And furthermore, that's still not enough. You still need something like linear or RKHS assumption on this function class. And taken together, these assumptions pretty much directly become equivalent to the well-studied linear MDP model, which imposes a low rank assumption on the underlying MDP dynamics, right? So therefore, this whole method would not be applicable if your MDP doesn't have a low rank structure. So the major challenge here is, can we move beyond linear MDPs and remove the restriction on MDP dynamics and also allow arbitrary and possibly nonlinear function approximation like neural nets? Okay, so to address this challenge, we propose a framework called Bellman consistent pessimism. Here is a very schematic illustration in the simplified bandit setting. What we do here is that essentially we fit the value function from data, and in the bandit case, it's just fitting reward function as a function of actions. And due to insufficient data coverage, we'll have a set of functions that are all consistent with the data, which we refer to as the version space. Okay, so then for any policy pi, we can then construct an estimate j height pi by looking at the worst case prediction at the initial state as 0 over the entire version space. And in MDPs, the version space is constructed by looking at all candidate value functions whose Bellman error on the data distribution is small. And the estimation of Bellman error can be is enabled by a standard variant of the Bellman completeness assumption that we've seen before. So this approach addresses both limitations of pointwise pessimism. First of all, it gives substantially less conservative estimates of J-pi. And second, we only require a version of Bellman completeness which does not impose structural assumptions on the MDP dynamics or the function class, which means that regardless of what the underlying MDP is, this approach is applicable. Okay, so this is all great, but we only have statistical guarantees, right? And in fact, sorry, I forgot to mention that although our approach is designed for the most general case, when we instantiate our result in linear MDPs, we actually get improved rate compared to prior work specialized to this setting. Okay, but so far, this is all good, but this is only a statistical guarantee, and it's unclear if we can even implement this algorithm efficiently. Okay, so recall that solving this constraint optimization problem that we show here in the side is only for estimating the pessimistic return of a single candidate policy, and we need to put a further argmax over all policies in front of it, right? And if you convert the entire problem into a big Lagrangian and fully expand everything, well, guess what? You get a monstrous optimization problem that is max, min, max, and we have no idea how to do it. Okay, so in fact, version space-based algorithms are no stranger to RL theory, and so is the headache caused by their computational intractability. So we mentioned this pessimism, optimism sort of symmetry earlier. And in fact, you can just flip the min to max and you can get a template for optimistic algorithms in online RL, right? And in fact, these version space-based optimistic algorithms enable some of the most general statistical results in online RL, which I'll touch on a little later, if time permits. But some of them are provably intractable, even under very strong computational oracles. In contrast, when you have point-wise uncertainty quantification, and which handles online and offline RL in very similar ways, it imposes many assumptions, but the computation required is just linear regression. So it's actually fully efficient, which is a very appealing which is very appealing, right? So for a long time, our understanding of version space-based algorithm versus point-wise uncertainty quantification is that there seems to be some kind of computational statistical trade-off, right? If you have more general statistical guarantees, then it's likely that it's gonna be hard, computationally difficult to implement it. So the surprise here is that we can actually break this trade-off in offline RL. At the first glance, the version space algorithm for offline RL is more difficult because instead of max in online, we got max min, right? Max min in offline. However, it turns out that this max min structure induced by pessimism is actually a blessing, not a curse, because this allows us to use the so-called no regret plus best response scheme from online learning to obtain an article efficient algorithm where the article itself is fully efficient in the linear setting. Okay, so and as a final piece of result, as we develop these theoretical understanding, we also talk to practitioners who are interested in applying RL to real-world problems and to see what concerns are holding them back and how we can address them. Right. So one major issue we learned is that it seems very difficult to convince someone to switch to RL trained agents when we lack robustness guarantees. Okay. So taking network control problems as an example, uh, the status quo there is usually a heuristic control rule. While they may not be optimal and have room for improvement, uh, they are time tested and very reliable, right? So in contrast, RL training is known for its instability, which is further amplified by the difficulty of hyperparameter tuning, which we talked about earlier. And with misspecified hyperparameters, it's very easy for RL to produce a policy that is even worse than the current policy, right? The heuristic control rule. So for this reason, some researchers advocate imitation learning as an alternative to offline RL, which directly learns and mimics the data collection policy, right? So it is very robust. However, due to its imitation nature, it can't produce a policy that is significantly better than the data collection policy. And in contrast, RL has the potential of improve towards or even reach optimality under certain conditions. Okay, so while imitation learning can be a great choice for automating high quality human decisions like in self-driving, in the scenario of network control, it makes almost no sense because the current policy that we use to collect data is already automated, right? They are cheap control heuristics. There's really no reason that you would imitate such a policy. So you do want to improve over it. So you have to use RL, right? So the real question is, can we actually have the best of both worlds and combine the robustness of imitation learning with the optimality of RL? Okay, and this brings us to our follow-up work in SML22 called Attack, which provides a positive answer. So recall previously we tried to construct the tight lower bound of JPy. Now, what we do here is that we simply subtract a constant in the objective, which doesn't change anything for now. And the constant is the performance of the behavior policy, the data collection policy. Okay. And we call this relative pessimism because it considers the performance difference between two policies. And by combining our Bellman consistent pessimism derivations with the widely used performance difference lemma, we're able to derive a concrete algorithm that formulates offline RL as a stackable game. And without delving into too much details, I want to highlight that the nice thing about this algorithm is that when the Lagrangian multiplier lambda, this purple lambda here is 0, you only have the algorithm in the red box. And turns out that this is a two-player zero-sum game, which is exactly a form of adversarial imitation learning. Okay, so and here the main player Q hat pi can be viewed as a discriminator that tries to distinguish between the data policy and the learned policy. Okay, so this gives us the desired robustness guarantee that pi is never significantly worse than the data policy pi d under relatively weak assumptions required by imitation learning. On the other hand, when this lambda term is present and lambda is properly chosen, offline RL guarantees kick in, and we obtain exactly the same kind of statistical guarantees as the previous pessimism, version space-based pessimism work. So this allows our learned policy to simultaneously have robustness guarantee against the data policy, as well as the potential of significantly improving over it. Okay, so we also actually implement the algorithm and achieves so the performance at the time in deep RL benchmarks, and we empirically show the relative pessimism's robustness with respect to this choice of the hyperparameter lambda. Okay. So that's pretty much the technical contents of the talk. And in the final few minutes before I open the floor to questions, I want to very briefly touch on other directions of interest in case anyone is also interested in related topics and happy to chat later. So in this slide, we briefly touched on online RL, and we mentioned the version space-based algorithms give most general statistical results in online RL. Now, the game here is that having an algorithm is not enough because unlike supervised learning and offline RL, in online exploration, there are lower bounds showing that sample complexity can be exponential in horizon, even when the function classes have low complexity. So what's really important is to identify structural assumptions in online RL to allow for tractable exploration. And in 2017, my collaborators and I identified low Bellman rank as a general condition for tractable exploration. And this has since inspired many follow-up developments in the community, which I've also contributed to over the years. And here we are, we have this whole zoo of online RL settings, and you can find more on this topic from relatively recent Fox and Stock tutorials. And I'll skip this part. And other new and emerging directions I'm interested in include extension of RL beyond the single agent and Markov setting, and in particular, multi-agent RL theory as well as RL under partial observability. And this is strongly motivated by network management applications, which I mentioned earlier. I'm part of the US NSF AI Institute on Edge Networks, where we're seeking to apply RL to manage and improve the operations of next generation edge networks. And here you have a massively multi-agent problems, and no single entity like a router, a base station, and so on have observability of the whole network state. Every single entity making decisions only have access to very, very limited local information, giving rise to partial observability. And my group has already started, working on these directions, and we have some very exciting recent works. Okay, so that's all I have, and all these works are, can be won't exist without my brilliant students and wonderful collaborators, and also thank you for listening, and happy to take any questions.
Thank you for the very informative talk, filled with lots of ideas. So there's time for a few questions from the audience. Yeah, go on here.
So first of all, thank you, Professor Jain, for this wonderful talk. So in the first half of the talk, you were talking about this function selection and trying to see how to identify a function that is close to Q star. My understanding is that there you are working, with the Bellman error and sort of identifying a function which is close in the Bellman error. So I wanted to know, in the tabular setting, one knows that the function that minimizes the Bellman error also leads to the optimal policy. But in a function approximation setting, do you think minimizing the Bellman error would also lead to a better policy? Thank you.
Yeah, that's a great question. So the answer is twofold. The first is that I think, as you're probably alluding to, Bellman error is only a proxy and surrogate for Q star itself, and Q star, whether you're close to Q star, is yet another surrogate for whether the induced policy is near optimal, right? So it is very indirect. There will be looseness in between, but the problem is that that's pretty much the best we can do. because the real data you get is just transition tuples, right? State, action, reward, next state. So the only thing you can possibly check is something that is one step, right? One step consistency. If you want to do anything multi-step consistency, you run into the problem of multi-step importance sampling. Okay, so that's the first question. First part of the answer. The second part is that in tabular, we often have this. If you look at the tabular theory, it's often these infinite norm bounds, right? That says like if the Bellman error is smaller than epsilon in infinite norm, then the function is close to Q star up to the same error divided by like a horizon, right? 1/1 minus gamma. Again, infinite norm. But these infinite norm guarantees are pretty much meaningless in large state space with function approximation because with so large a state space and limited amount of data, when you don't see when many states you don't see even once, there's no hope to minimize anything, to minimize the infinite norm of any loss function. Okay, so any loss you minimize there is always an average loss, always an expectation. So that actually gets us to the second half of the talk where all the modern analysis of reinforcement learning in the function approximation setting, we never use infinite norm again. It's always some kind of uh, uh, expected loss under certain distributions. And we spend a lot of time thinking about these distribution shift issues, right? So this coverage that we talk about in the second half precisely arise because when you minimize Bellman error on the data distribution, and you look at what happens when you actually use the learned function, right? Like when you use it for evaluation, when you use it to induce a near optimal policy, you look at the accuracy of the prediction, you look at the performance of the induced policy, there will be a distribution shift. It's kind of like you have a training distribution, which is your data, and there's sort of a test distribution, right? For example, in the case where you just run the induced policy, the test distribution is essentially the states you run into when you actually execute the learned policy. So that distribution shift, but then we have all these coverage, these language, new concepts that allows us to handle these. So the way that we analyze these, how Bellman error translates to the final guarantee is quite different from how the tabular analysis did it.
Okay, thank you. Maybe I will ask one more question. It's again on the first part of your talk. I think you considered the problem where you have a finite number of potential functions, one of which is the true Q star function. Now, in many of these function approximation settings where you're actually getting these candidates from a fitted Q iteration passed with some hyperparameters, right? It's probably quite likely that none of these will exactly be equal to Q star. They will all be some approximate versions. So it looks
so the actual paper handles approximation. So I just didn't talk about it. So it's so and actually in all these function approximation analysis, actually handling approximation error is usually the routine part. Like it's actually once you get the generalization analysis done, handling approximation, there is some very rare exceptions, but most of the case is very standard routine to handle approximation. The reason is because if you look at the analysis, it's essentially just two parts. One is like you control something like the Bellman error, right? And if you're exactly realizable, if you're, you have exact Bellman completeness, those are just controlled by the estimation error, the general statistical learning like estimation error. Like that part has no RL in it. It's just like generalization bounds, right? Like Hovden plus union bound, like VC theory, that kind of thing. And then from there, you have these like error propagation analysis, which is the analysis I was alluding to the previous question. And that part is like fully RL, no estimation and whatsoever, right? And when you have approximation, typically what happens is that just some additional error will get added to those estimation error. But how they propagate to downstream, like do this change of measure, change from training distribution to test distribution, that part of the analysis is exactly the same. So it's just like add some number to the analysis and that's it. There are exceptions, and there are also some interesting cases where what kind of norm do you measure the error and so on becomes tricky and nuanced. But if you just want a relatively loose and legitimate bound that can handle approximation, it's usually pretty easy.
Okay, thanks a lot. With this, we'll conclude this talk. Let's thank Professor Nanjian again.
Yep, thanks.
Thank you very much. So we'll continue now with the next talk, which is the second part of Professor Sridhar Mahadevan's lecture. Over to you.
Okay, thank you. So that was an excellent talk we heard. It's the perfect introduction to what I want to say, which is a general strategy of research that I have followed for many years is always look for the null space. This is a linear algebra analogy. For those of you who know linear algebra, you have a matrix and there's a space that the matrix spans, which is all linear combinations of its columns. But then there's a null space, which is sort of all the vectors that the matrix sends to the zero vector, basically. So in other words, in terms of research, look for things that people are not doing. To me, reinforcement learning for the last 30, 40 years has been struggling with the concept of function approximation, how to combine function approximation and reinforcement learning, right? The value function approximation problem. And when you mix in things like the gradient formulation of TD, things get difficult very quickly. And I don't think this problem has been satisfactorily resolved, even though there's a lot of excellent work, as we just heard. So I'm going to take a fundamentally different approach here. And it's a different approach in the sense I was talking yesterday. We have to change the way we think about machine learning. To make progress, we have to start by rebuilding, and we rebuild from the foundations up. So I will start by showing you a little bit of how I think about machine learning in a different setting. I want to finish up something I started yesterday on how to think about deep learning in terms of categories, and then I'll get to co-algebra. So that's sort of the plan. So this idea of machine learning can be viewed in terms of imitation games in the following sense. So remember, ChatGPT or GPT-0, excuse me, is this sort of package that you can type in text and it'll tell you if it came from a human or a machine. So how would you build a GPT-0? Well, presumably what you would do is you would take samples of text written by humans, and you would say, you label that as coming from a human. You would take samples of text generated by a large language model, and you would give that. And then the red points are sort of the test, right? This is classic function approximation. Now, there's an enormous literature in machine learning, in statistics, optimization, and related fields of information theory on how to solve this. So I won't even bother trying to cover this. And you've all taken classes in machine learning. How do we start with a completely different approach? Right? That's what I'm interested in. So we want to learn functors. We do not want to learn functions. Now, there's a good reason why we want to learn functors. The reason we want to learn functors is there are canonical solutions and they have universal properties. No such result exists for learning functions. And that has to do with the math. Okay, so let me explain how this works. So imagine I have a data set, which I can view as a category, as a collection of objects, training data, right? And some relations between them. And my goal is to construct a functor that produces some output, like the one we just saw, maybe some labels. We saw clustering can be treated as a functor, right? So the input is some finite metric space, the output is the partitions of that space. So we have a sample functor. Now, the goal of machine learning is from this data set and the sampled function, we want to construct a new function or functor that is over the whole category, over the whole space. So if our category was Euclidean space, we get points in the space, we get output for those points, and we want to extend it to the whole space. But we want to do this in a way that tells us that we have a canonical solution. And in category theory, this means what is the universal problem? Now, if you ask this question of all the work in machine learning, there is no answer. If I say, I give you samples of a function on some set, now tell me the value of the function on the whole set, there is no canonical solution to this problem. What people do is some sort of regularization. They say Occam's razor, minimum description length, some sort of Bayesian solution. I mean, it goes on and on and on, but there is no canonical solution. So in order to rebuild machine learning from the ground up, we have to start with a different approach. So first we say we don't want to learn functions, we want to learn functors. Why do we want to learn functors? Because we have canonical solutions. And that comes from this very beautiful idea called a Kahn extension. Very, very famous mathematician named Kahn. So what exactly is a Kahn extension? So a Kahn extension goes like this. You have some functor, say strip F, that maps a category C to some other category E. So in our example, for example, this could be the data set category that which you have the data for, right? And what you really want to do is you want to extend this functor to not just see the data, but to the entire space on which you want the function. So let's assume that the sample data is embedded in the entire space, which is typically what we see. Then there is a very general solution. In fact, there are only two possible solutions to this problem, which is called the left Kahn extension and the right Kahn extension, and they satisfy a universal problem. So this is how we rebuild machine learning. You have to start with a mathematically well-founded solution to the problem. Right? Otherwise, you're sort of always looking around for some solution, and it's always you add something to it. So what does this Kahn extension mean? Okay, so we say we want to extend the functor f along the functor k. So f is going to be extended along k. What does that mean? We have to fill the gap between D and E because we don't know what that is. That's the left Kahn extension. Right? So what does it mean to fill the gap? What it means is we want so everything in category 3 composes. So we can compose functors, right? So if I compose this missing functor, left Kahn extension with kappa, right? Then I get a functor that maps from C to E, right? This is what I want. This is the solution to the machine learning problem. But am I going to get exactly the original functor back? Or match that? Well, no, because that was on sample data and they're not going to match. So what can I do? So I said there is some natural transformation that will map this to the composition of the left Kahn extension and kappa. Okay. And it must satisfy a universal property. What does that mean? If there was any other functor that filled in this gap, So imagine I have some other function called H. So H fills in this gap as well. So if I compose H and kappa, I get another solution. That solution must be uniquely decomposable into the solution I just constructed. So that means if there was some other universal transformation from F to the composition of H and kappa, let me call that gamma, then gamma must be uniquely decomposable in terms of eta, which is original natural transformation. That's what it means to satisfy a universal problem. So the left Kahn extension gives me one solution. The right Kahn extension goes the other way, where the natural transformation goes from the composition of these two, which is the composed functor to the original sample. Right? These are the only two solutions that we can get. Now, what is absolutely remarkable is that every single idea in category theory follows from this. Every single idea. Another way to say it, which is even more dramatic, is every single idea in mathematics comes from here. This might seem amazing. Probability comes from here. Topology comes from here. Anything you want. Okay? Cartesian product of sets comes from here. So no such thing exists in anything else in mathematics. This is, as far as I know, completely unique to category theory. The fact that you have one construction that explains all. So yesterday I talked about the Onega lemma. Remarkably, the Onega lemma comes from this. So this is why we can rebuild machine learning and AI if we start with completely new mathematics, right? And because we have unique extensions of functors, I think there's hope that we can rebuild machine learning. Okay, now.
Could you give an example? It's a probability.
Yes, it's a great question. Okay, how about an example? Now, to go from here to the example is going to require some work, and I'm going to do that today and tomorrow. So bear with me. But I should tell you, Rome was not built in a day. That's the famous saying, right? So we build it brick by brick by brick. So there's a lot of gaps that need to be filled between something like this and probability. So I have to introduce things like codensity monads and stuff like that. So what I'm trying to say is, yes, we can show that much of math can be derived from here, but the process of showing that is not easy. It's there, it has to be understood, it has to be built on, and I'm going to try to show that. So I just want to make sure I start at the beginning with telling you why is this approach different? There's been a lot of wonderful work in machine learning over the last 40, 50 years, but it's all been predicated on approximating functions. And in order to change the game, you have to start with a blank slate, right? This is how we start. We say, no, we're not going to functions, we go to functors. We're going to do functors because we have property relations. We are building on a different foundation. Right? So this is one way to understand this. Yes.
So you can give an inclusion why estimating a functor will be more easier or efficient than estimating a function.
When you say easier, I don't know. I haven't said anything more easier. I'm saying here I have two canonical solutions. So I can take any number of problems and say, does this correspond to a left Kahn extension or right Kahn extension? So, okay, here's an example, right? So I talked about UMath. This is a Python package you can download today, run it. It scales, it runs on millions of data points. It's very fast. It's the best data visualization method today. It's a Kahn extension. That's a good example for you. If you go read the UMath paper, run the code, what you're doing is computing a Kahn extension. They construct a functor that maps your data set to a topological space and the adjoint to that functor. And by doing that, you reduce dimensionality of the data. And it works amazingly well. It's far, far better than Jeff Hinton's stochastic neighborhood embedding or t-SNE, right? And it's built on this technology. So we know how to do this in special cases. I'm saying this is much more general. We can do many other things. We can do reinforcement learning with this stuff. Well, we have to understand the math, right? So. Okay, so getting back to deep learning. So, yeah, sure.
So just to make sure you're saying that the data that you read them as members of the categories.
Yeah.
And you're saying that the labels now live as members of another category with description.
Yeah.
Right? And the F is a function that relates to them. Is that something given for?
Yeah, this is, I'm saying, of course, this theory does not apply to machine learning. It is a general theory. It says for any functor, now I should mention, it is not the case that Khan extensions always exist. There are conditions in which a Khan extension exists, and they have to do with things like, for example, what sort of category does E form? Does it have total, is it a complete category and things like this? I don't want to get into all that. But so this is not a magic solution, but we know the theory. It has been well developed, well understood. We know exactly when these extensions exist. The important point I want to try to emphasize here is that we're starting with the property that there are only two canonical solutions. Yes, and there are two, and they correspond to things that people have already done. So, for example, if we go to probabilities, we can represent those as Khan extensions. If we go to topology like UMAP, we can represent that as Khan extensions. So what I'm saying is this is a very overarching framework that says, look, these are two ways to think about the problem, and what people have been doing correspond to these two things. But we understand the general theory, there may be a vast number of new things we can do. It's just that we don't understand the theory, we haven't studied it yet, right?
From a theoretical perspective, this would make things more fun size different.
Yes, and I'm going to explain. Yeah. Okay, so this is a very beautiful paper for those of you who want to understand category theory in the context of something like deep learning. I highly recommend it. It's written by 3 people at MIT. Brendan and David are now in the Bay Area at a category theory in an institute called the Topos Institute, which is somewhat close to Berkeley. Now, what they do in this paper is they take deep learning and say, how can we treat deep learning in terms of category theory? How can we come up with a framework for compositional learning? And what they end up doing is a very elegant sort of formulation of deep learning, which you can then sort of extend in many different ways. And I'm going to talk about how Gaia builds on something like this. So let me introduce this idea of a monoidal category. So categories in applications typically tend to be monoidal. For example, if we do quantum computing, remarkably, quantum computing is just computing with a category. So once you understand category theory, not only can you do computing with a classical Turing machine, you can immediately understand how to compute with a quantum computer, because you just go to what's called a closed compact category, where you can take things like teleportation, quantum entanglement, and represent that as things in the category. And immediately you can do things like quantum reinforcement learning. It's amazing. It can be done in theory, because you have to run it on a quantum computer. That's a different problem, right? So the power of category theory is that it gives you this abstraction, right? So what is a monoidal category? You have a product, so you can take two objects and multiply them. So obviously sets are monoidal because I can take a Cartesian product of two sets. Vector spaces are monoidal categories. I can take the product of two vectors. Topological spaces are Cartesian categories. I can take product of two topological spaces, and so on. There's an identity element which says the product of one and any object is isomorphic to the object. So an important property in category theory is you banish the equality sign. Just imagine a t-shirt with the equal sign and something across it. No equality, okay? No more. So we're only going to talk about isomorphism. When I say something is isomorphic to something else, which means there's an arrow that goes from here to here, and an arrow that goes back, such that the composition of the two arrows gives me identity, right? The identity object. Okay, so take unit interval on which you define probabilities. You can show that it's a closed symmetric monoidal pre-ordered. There is obviously an ordering, a total ordering on the numbers, real numbers between 0 and 1. You can take the product of two real numbers between 0 and 1. That's your product. You have the unity. And what is this idea of closed? Closed means there is an adjoint to the product, which is a division operator, right? So I can always take the ratio of two real numbers between 0 and 1. I have to be careful though, because it has to be between 0 and 1. So it has to be defined as truncated domain, right? And you can do that. Okay, now the other thing you're doing typically in applications is you look at enriched categories. That means, remember, I said for any two objects in a category, there is a collection of arrows that go from A to B. Now, I talked about those collection of arrows as being a set yesterday. Let's think of that as not just being a set, but as an element of a monoidal category, right? So for example, it could be a distance, it could be a probability. So it could be something that has more structure. It could be a group. It could be something that has a topology to it. So enriched categories are categories where the collection of arrows between two objects forms a different category, something with structure that you can exploit. And this is what Fong and Spivak do in this paper. Okay, so here's how we're going to deep learning as a category. We're going to define a symmetric monoidal category, learn, where the objects in this category are sets, which represent sort of roughly parameters in your neural net, and the morphisms represent learners. Okay, so here's the definition from their paper. The symmetric monoidal category learned is defined as a collection of objects. It defines sets, a collection of equivalence classes of learners. Each learner is defined by the following four tuple, right? A parameter space, which is a set, say, of real numbers or vectors. This is the weights of a neural network, or the inputs and outputs. It's typically the weights of the neural network. An implementation function. Now look at the way they abstract this, right? An implementation function. What does this do? Given a parameter, the weights of your network, given the input to your network, it produces an output. Okay, simple. An update function. Now, this is your deep learning update, but we don't want to talk about deep learning. This is abstraction, right? So what does it do? Given the weights of your network, given an input, given an output, it produces a new set of weights. This is what the learning step does. Okay? We abstract out all the details of what the learning step might be. We don't care. And this is the most interesting thing. The request function. What is this function? This is what you need to make things compositional. Remember, we want to treat a machine learner as a black box. I got this black box, it does its thing. I got another black box, I want to stick them together. So for that, you need the request function. What does the request function do? Given the weights of a network from P, given an input, given an output, I give you back another input. What does the intuitive be? This is like the back propagation. It says, if you had given me this input, it would have helped me. Okay, this is sort of message passing that you go back. So here's the structure, right? So a learner is defined as a morphism to the category where you have an update function that takes a parameter and these input outputs and produces a new parameter, right? The request function takes an input and an output. So if you read it from right to left or left to right, depending on how you want to read it. The request function takes an input and an output, the actual input and output, and says to the learner before it, this is the input you should have given me, it would have helped me. We haven't said anything about backpropagation yet. This is still abstract. You'll see how backpropagation emerges when we start putting in sort of stuff. So think of this as a sort of a high-level programming language. Yeah.
So why do you want to consider a monoidal category?
Because we're going to products. So here's why. So we're going to take these black box learners, morphisms, we can stick them in parallel or we can put them in sequence, and we're going to form products of them. So that's why we need the monoidal category. Okay. So what they do, this is a string diagram. So a string diagram in category theory is extremely helpful. It's a visual way of plugging in things. It's like a wiring diagram. And it's remarkably general. It's much more general than graphs because you have things like braids, you can have ribbons, you can have tangles, all this exotic stuff. And it turns out in quantum computing, you need braids. Braids are like when you have crossovers of wires like this. If one wire goes below another wire or it goes above another wire, it makes a difference. So this is called braiding. You can have ribbons, you can have tangles, all kinds of cool stuff. So anyway, here we don't need all that exotic stuff. So what is this saying? This is saying if I have two learners and I'm going to stick them in sequence, right? So this one is defined by its update function U and its request function R. This one is defined by its update function V and its request function S. I need to somehow figure out how to combine them so that I can put a black box around this and now have composed learner. Similarly for the product case, right? We have two in parallel. Let me work through the equations for the sequential case, right? So here's the idea. Now we have two learners, right? Each is described by parameter P, implementation function I, update U, request R. That's the first learner. It feeds into the second learner. That has parameter space Q, implementation J, update V, and request S, right? And we want to compose those so we get a black box which has input A, output C. So in order for this black box to be defined, I need to know what its parameter, implementation, update, and request should be. So let's look at each one of those. The parameter is easy because this has parameter P, this has parameter Q, so we need P times Q. So we need monoidal right here. I have to take a product of these parameters, right? That just says that if I have a bunch of neural nets, like a bunch of transformer units, then the overall parameter space is the product of the parameter space of each transformer building block. It's easy. So I need the composed implementation functions, the composed update functions, the composed request functions. So let's look at this. This is the easy case. What is the composed implementation function? Very easy. I take the implementation function for J, that takes a parameter Q from little q from big Q, and the input of the first learner. So this is easy. So this is obvious. You just feed in the input from the first learner to the second learner, the second learner does its computation, sends it out. Okay, easy. Now let's look at the composite update function. This is a little bit more interesting. So what's going on here? So this is the easy part. Easy part is, what does B do? So the second learner. The second learner says, I take my parameter, I'm going to compute. So remember, the update function takes a parameter, an input, and an output, and returns a new parameter. So what is the input to the second learner? Whatever the first learner sends it. What is that? The implementation of the first learner times its parameter and its input, right? And then this is the output. So we've got this piece. Now what about this piece? This piece is the really interesting piece. How should the first learner work? Well, it's saying, I know my parameter, I know my input, I don't know what B is. This is the hidden unit problem in deep learning, right? You don't know what the intermediate stuff is supposed to be. What do? You simply say, I look to tell me, the downstream learner from me should tell me what input it wanted. That is the target output I'm going to train for. So what is that? That is the request function from the second learner, S, of its parameter, the implementation value that I send to it, and the final output, right? So as far as this guy is, he doesn't see C because that is much further downstream. He only sees the computation of the request function from the learner next, right? So this is the composite update function, and this is the composite request function. And again, you can follow the same logic here, where you can show the request function for the whole thing can be done from the request function for each piece. Now, what is beautiful about this is shows you how to abstract out the property of compositional learning without specifying anything about the update. We haven't said anything about backpropagation yet. We don't say anything about gradients. But because of this kind of structural formulation, we can now plug in anything we want. Right? That's the beauty of this architecture. Okay, so now let's bring in backprop. So what is backprop? So we've defined this category, the category of learner. Okay. So now we have this sort of general implementation function. We have this general update function. But we have to fill that in. This is how we do it. We define a functor that will basically say the update function is the original parameter minus some learning rate times the gradient of some error function and so on. Now we put in backprop. Okay, so when you define backprop as a functor, you can take this category, the category of parameters, which is every object in this category is the Euclidean space and a continuous function that maps one Euclidean space to the next Euclidean. Right? So we can now define the functor update over this category that maps to the learn category. Now we've got backpropagation. Similarly, we can do that for the request function. The request function basically implements the backpropagation backward pass. So you see how we have abstracted out backpropagation as a functor, but we have defined a very general category for learn. Now we can plug in all sorts of other things in it. We don't have to plug in backpropagation, right? We plug in whatever we want. So, for example, if we did backprop, we're using a first order oracle. But we could do something different. We could take any of the methods in Shalom's book, a zeroth order oracle with some stochastic approximation algorithm, we put that in there. So instead of going steepest descent, it does some, SPSA, like we have to stop on SPSA. We do some simultaneous perturbation, stochastic approximation. We do something else. So they all define functors, right? So we stick that in there.
Line with what you just said, how do you put in the stochasticity in what you do? Like stochasticity meaning, when you give in the inputs, the output that is being generated could be random.
Yes, but that is just part of the definition of the functor. You can put in anything you want. Right? The functor just says it's like a programming language. You can make it as complicated. You can put a Python program in there. It's okay. Remember, category theory, there is no constraints on what is a morphism. A Python program is a morphism. Why? Because I can take one Python program and compose it with another Python program. It's a perfectly valid Python program. As long as the output of the first one is compatible with the input of the second one, it works. Right? That's the beauty of category theory. It's highly modular, highly compositional. Morphisms and objects can be arbitrary as long as they satisfy these composition rules. Right?
Maybe you are going to consider that, but maybe working that type of definition is that given a task, we figure out the sequential compositions.
So how do we decide what the architecture should be? That's a different question, right? But before we even get there, we need to understand how do we do this in a more general sense. I'm using this as a backdrop to something I'm going to do with Gaia, which is going to generalize this. So I don't want to spend too much time on this because the good stuff is yet to come. Okay, so getting back to natural transformations for deep learning, what is natural transformations? Remember, they are the ways functors interact, right? So I have the category of parameters, which is the weights of a neural network. I have the category of learners, which we just defined. Now, backpropagation is one functor. Stochastic approximation is another functor. And then you can do anything you want. So as a simple example, there are very good reasons you should not work in Euclidean space, or at least in real value Euclidean space. For example, if you did backpropagation in the complex space, many things become easier. So this is a class you can't take in universal science. Go and take a course in complex analysis. Complex analysis is beautiful. It's much, much more well-behaved than real analysis. There's a fundamental change that happens when you go from real numbers to complex numbers. Everything gets more well-behaved. That's why so much of mathematics was developed with complex analysis, because everything is well-behaved. Functional approximation in the complex world is so much better than in the real world, right? And it just has to do with the nature of complex numbers. So we could define some category of parameters to be complex numbers, and then we would have a complex value backpropagation functor. But the beauty is we don't have to change the category of learners. It's still the same. We still have an update function. We still have an implementation function. We have a request function and so on. All we are changing is this from real value weights to complex weights, and we change our functor that is what the update procedure should be, right? And there are beautiful papers you can find on Archive on why you should do backpropagation in the complex plane. Because you can do one function called, stochastic approximation with single function evaluation, known to be a very biased kind of thing. But in the complex domain, that changes. In fact, in the world of numerical analysis, they do this. For very high precision design of engineering structures like airfoils and stuff, they do functional approximation in the complex plane, because the complex Taylor series is very elegant, and it tells you how with the first order approximation, it gives you much better behavior in the complex plane. So this structure helps you sort of scale deep learning even without getting into things like Gaia. Okay, now let me ground this about a little bit with transformers, right? So this is a very nice paper from MIT, Google, and so on. They show that transformers are sort of universal in a certain sense. What does that mean? It's not a very strong result, but it says for any function from a sequence of n symbols of dimension d each, so the input is Euclidean space of dimension n times d, the output is the same. There is a representation in terms of a transformer. It doesn't say the gradient descent algorithm will find it, but there is a representation. The one catch is transformers compute permutation equivalent functions. This is very important. So what this means is that if X is my input token sequence and P is any permutation matrix, the output of the transformer is the function applied to the original input and the permutation done afterwards. So in category theory, we would write this way. So if I permute the input and then apply the transformer function, or if I apply the transformer function and then permute, I come back to the same spot. So the commutative diagram. So you can use things like this to understand transformers. So what we're going to do is we're going to take this technology and we're going to generalize it. There is a little bit of derivation in the paper that shows why transformers compute permutation equivariant functions, and that has to do with the attention matrix, which you know is symmetric. And then you can compute, if you look at the original paper, they were very simple code to show that the actual function that a transformer building block computes is permutation equivalent. So we can define a category of transformer models where the objects are these token sequences, and the morphisms are this notation that's used in the paper, where you have H heads and so on and so forth. I won't get into the details, but basically you can define morphisms that correspond to transformer building blocks. Okay, so now we come to Gaia, right? So the one thing I haven't told you yet, so we have all the pieces, we have the sort of building blocks we need. We need one extra piece of thing, which is higher order category theory. So I have to introduce this category called the simplicial category. So think of the simplicial category as sort of the one-stop machine learning shopping center. You can do anything in machine learning with simplicial categories. And yet they're remarkably simple. They were originally invented in algebraic topology because mathematicians kind of got lazy, had to do all this complicated stuff. They invented simpler and simpler ways to do things. And one of the elegant things they invented was simplicial sets and objects. And it also forms a foundation of something called homotopy theory, which is actually very important in machine learning. So for example, when Spivak and Fong say equivalence class of learners, that's very important. What they meant was there's an invertible transformation from one learner, one morphism to another, such that if that is invertible, that morphism for one, those two learners are considered equivalent. What you really want is some notion of homotopy, which is like, in topology, you have this idea that why is a donut the same as a coffee cup, because it has only one hole, and you can sort of, think of it made of some sort of rubber or something, and you can reshape one into the other. That's sort of abstract homotopy. And so you can take equivalence classes of learners to be homotopically equivalent functions. Okay, so simplicity category, right? Now this is where India should take some pride. Why? It was built on natural numbers, right? What was India's great contribution to science? Like Bertrand Russell said, India has contributed nothing to science. Why nothing? Because zero came from India. Zero. Can you imagine what a powerful concept? So imagine you were in India in 200 BC or something, and you know about decimal numbers because we were using decimal numbers in India in 200 BC. And you take a trip to Greece, you meet some famous Greek mathematicians, right? Euclid, Pythagoras, who else? And you say, what's wrong with you guys? Why are you using this Roman numeral system? And they say, well, what's wrong? It's perfectly fine. And you tell them, you don't have zero in the Roman numeral system. And they say, what is zero? You try to explain to them what zero is, right? So you see how there's a fundamental shift when you go from Roman numeral system to decimal number system. So category theory is like that. It's fundamental shift in thinking. So what is the simplicial category? The objects are ordinal numbers, right? Numbers from 0, 1 to n minus 1. Now, the slight definition differences. Some people view it as 0 from 0 to n, or n minus 1 doesn't really matter. What are the arrows? They are functions from one ordinal number m to another ordinal number n, such that they are weakly order preserving. So the ordinal number I is less than or equal to j, then the function of I is less than or equal to function of j. So here's an example. Here's the ordinal number 0, 1, 2. So according to this notation, this will be 2, bracket 2, bracket 2, open bracket, 2, close bracket, and this is ordinal number 1. Okay, and this is weakly order preserved because why? Because clearly 0 is less than or equal to 1, and the output is 0, so 0 is less than or equal to 0. So it turns out this is all you need to do topology. Isn't that amazing? It's like kid stuff. You could teach your high school or maybe an elementary student this, and now they can do topology. Isn't that amazing? So how does this work? So we're going to construct contravariant functors. So essentially, it turns out that all the morphisms I just showed you in the previous slide, right? These morphisms from m to n, all of these could be built out of elementary building blocks, and these are basically the basic injections and surjections, right? So what are these? So if I go from ordinal number n to n plus 1, this is an injection. Injections are one-to-one mapping. So here there are, say n things, here there are n plus 1 things. So how do I do a one-to-one function? I have to skip some element. So this says skip I. So 0 goes to 0, 1 goes to 1, so on and so forth. But when you come to I, you will go to I plus 1. So you skip I in the range. Okay, this skips I in the range. The opposite is the elementary surjections or onto functions. Here what you do, you start with n plus 1 elements in the domain, but you only have n elements in the range. So one element in the range must be hit twice. So two different elements in the domain must map to that element, and that is I. So these are the elementary injections and surjections. We are going to contravariantly map them to the category of sets. So this is our contravariant, this is our simplicity of sets. So that means we start with this category, but we do the opposite of the category, which means we flip the arrows, right? So any category C, if I do C op, I flip the arrows. If the arrow goes from one way, I flip it. Okay. So the flipped category to X. X here is some set. So this gives me simplicity of sets. Simplicity of sets are more general than directed graphs. So it's very simple to show that you can just do 0, 1, 2, and you basically get all of directed graphs. Okay. So all the extra stuff you get is not possible to do in directed graphs, which is why Gaia is more powerful than deep learning, because deep learning you only deal with graphs. You cannot do anything beyond graphs. Okay, so this is showing you how many primitive injections are there and how many primitive surjections are there. And then these can build up, so like a combinatorial factory, you can build up all possible functions. Now the real trick is we're going to take this and we're going to map it to some rich category, some enriched category, then we can play with that in sort of different ways. So I wrote a paper called Universal Causality in the journal Entropy, but I use the simplicity category to do causal inference. You know about Udea-Pulse work, it's about taking a directed acyclic graph, and causal inference is like conditioning, it's not conditioning, sorry, Udea will kill me if I say conditioning. It's basically artificially changing the value of some variable to some fixed value, and then all the input arrows get deleted. And that deletion process can be done with simplistic categories. So I use this to generalize Udea's work from graphs to simplicity of sets and objects. So now I'm going to map this back to deep learning. So we're going to construct the nerve of the category. What is the nerve of the category? Category is defined as a collection of objects, a collection of arrows between pairs of objects. Simplicity of set is a contravariant functor mapping the simplicity of category to a category of sets. The simplicity of sets are more general than categories, right? That's why the basis for higher order category theory. So, but I can construct a mapping, a functor which is completely faithful from the category, from any category to a simplicity of set by constructing its nerve. And it's very simple. Category is just collection of objects and arrows. So just consider arrows of length 1, 2, 3, 4. So you're saying, look at all ways in which I can compose morphisms, right? Every which way I can compose morphisms gives me simplicial sets of higher order. So the 0th order simplicial set is just the objects of the category. Simplicial set of order 1 is just the arrows. Simplicial set of order 2 is all composable arrows of length 2. So you go from A to B, B to C. All ways of doing that, every triple of objects. And then 4, 5, 6. So I can embed standard categories as simplicial sets. So we can now construct the nerve of the category of transformers. Transformers are morphisms. I can compose the morphisms, and I can form a simplicial set. So I can take all the stuff that people in the LLM world do, and I can say, well, that's just a category of simplicial sets constructed from the nerve. But it is not as powerful as simplicial sets, because while the nerve functor that maps a category to a simplicial set is full and faithful, so you can do all the things, it's like a copy of the category in terms of simplicial sets. But when you go back, you lose structure, right? You cannot fully capture what a simplicial set does. So if you build a theory of deep learning on simplicial sets, in theory, you have something more powerful than what deep learning can do. So that is sort of the high level idea behind Gaia. Okay, so and this just is what I just said. So that's all I really wanted to say about this. I wanted to shift talking about coalgebras. And for Gaia, you can find a full description of the details that I didn't go through on this fairly long paper on my IISc webpage. There's a lot of details missing from here too. It's forthcoming book, which will hopefully come out maybe later this year or next year, where I'll have a lot of more details and I'll fill up all the gaps that I haven't done yet. But I wanted to give you the high level idea of why, how this works. Okay, so now we're going to shift to talking about how we're going to build sort of new families of generative models, and we're going to use this idea of a coalgebra, right? So what are generative models? Well, we can go all the way back to finite state machines, Markov chains, Markov distant possibles, form DPs, predictive state representations, linear dynamical systems, context-free grammars, sequence models. Every one of these is a coalgebra. Right? So what is a coalgebra? A coalgebra is a functor, but it's an endofunctor. What is an endofunctor? It maps a category back to itself. So here's a coalgebra, very simple. Take an object X in the category, F is a endofunctor, it must produce back some new object in the category. That's it, that's a coalgebra. Every generative model done in computer science in the last 60 years is that. Okay, so this gives you an incredibly powerful way to think about a very large class of models. So coalgebras generate search spaces. So anytime you look at game trees in Go or anything like that, they're all coalgebras. So what's the difference between a coalgebra and an algebra? Algebra goes back. Algebra is f of x goes to x. Just flip the direction, you get algebra. You go the other way, you get a coalgebra, right? It's very cool, very simple. So I want to show you a little bit about how this works. The other big idea here is the foundation of machine learning has been induction. This goes all the way back to philosophers like Hume and even further back. Induction, you see the sunrise in the morning, you see the sunrise in the morning, the next day, the sunrise in the morning, so you say, every day the sun rises. This is induction. But there's a beautiful idea called co-induction, which is much more recent, comes from a breakthrough in set theory. So the work in inductive inference led to this formal model of machine learning developed by Gold, Solomonov, later extended by Vapnik and Valiant and many others. It relates to stuff in algorithmic information theory by Chaitin, Kolmogorov, minimum description length, Occam's razor, all of this stuff. This is all based on the principle of induction. We want to fundamentally change that by looking at co-induction. This is a new paradigm because generative AI is all about infinite objects, Reinforcement learning is about infinite data streams. We shouldn't be modeling infinite data streams with induction. That's why I don't think the approach of functional approximation as we have studied it is the right approach. You need co-induction. Okay, so why? Because the Fabada grammars, MDP, everything, they're all infinite data streams. You need mathematics for infinite data streams. And why do you need new mathematics? Because they're non-well-founded sets. They violate the basic Zermelo-Fraenkel with axiom choice. So it's called ZFC, axiomatization of set theory. There's a well-foundedness axiom in set theory that says you cannot have a set with an infinite set of memberships. That's not allowed in set theory. But if you look at standard data structures, like an infinite list, an infinite tree, that violates the principle of well-foundedness. This was a huge problem in computer science. And in fact, this work was motivated by computer science because they said, how can we compute with these infinite objects when they violate set theory? So Peter Axel, who's a mathematician who sadly died recently, came up with a brilliant idea of how to model infinite objects as graphs, called it accessible pointed graphs. And he developed the principle of co-induction. So there's a lot of beautiful work that describes all of this. I'll give you some examples. Bratton is a very major figure in the sort of developing this theory. There's lots of papers on this. So the method of co-algebra, exercises in co-induction. This is a nice reference. There's lots of work on how to do various kinds of modeling of automata, dynamical systems, many other things in terms of this. So I don't have to go through all of this. I recommend you read this. I'm just going to give you some examples. So here's the lesson for reinforcement learning, right? So non-well-founded sets are sets that have basically infinite membership chains. Right? Think of an infinite data stream, right? Transform model or reinforcement learning agent, something like this. We're going to use the category theory framework with universal co-algebras. And co-induction generalizes all the fixed point theory we've used in reinforcement learning so far. All the Banach fixed points, all of those are special cases of this idea of co-induction. So the high-level message is reinforcement learning is metric co-induction in a stochastic co-algebra. That's it. From a category theory point of view. Why? Because it gives you new tools, new ways to think that we haven't understood before. Because we didn't know the math, we didn't use the math. So again, beautiful book by Bart Jacobs on the mathematics of state and observation. This sounds like something reinforcement learning people should know about. How many people have read this book? See, here's the problem. And you know where this comes from? Computer science. How is it that computer science developed this and reinforcement learning people, machine learning people don't know this? Isn't this a problem? We're in the World Wide Web, right? Information is supposed to be instantaneous. You can ask them, why don't we know this? I'm not blaming you, I'm blaming myself. Like, why didn't I see this before? I've been doing this for 30 years. How come I don't see this stuff? Anyway, better late than never. So this is a lovely book by Bart Jacobs. And this is a great paper, very long paper, about 70 pages on a new foundation for dynamical systems as co-algebras. So I highly recommend. Now you can extend all of this to the stochastic setting. This is a beautiful paper by Anna Sokolova, who teaches in the University of Salzburg, both Salzburg. And she shows you how you can build stochastic process models as co-algebras. And here's a very long list of co-algebras that correspond to various kinds of systems. Like a Markov chain is a functor that is called the distribution functor. It takes a state, produces a distribution over all states. And that's a functor called the distribution functor. In category theory, probabilities are defined by monads because because you can multiply and add probabilities, they form an algebra. So algebras are defined as monads. There's this incredibly rich thing. For those of you looking for research, some of you asked me yesterday, thesis topic. Here's your thesis topic. Okay? Figure this out. Figure this out. This is great. This could make your career. You could become famous. You can send me an email thanking me later. But this is a gold mine of new ideas waiting for people to develop. Okay, there's this beautiful idea of a final co-algebra. Remember, co-algebras are x goes to f of x. F is a functor, x is an object, right? X goes to f of x. What is a final co-algebra? A final co-algebra says you can go the other way. right? So there is a beautiful result that shows that in a final coalgebra, X is isomorphic. This is the generalization of fixed point theory. So in a final coalgebra, you can go the other way. So there's a very nice theorem by Axel and Mendler called the final coalgebra theorem that says for a very wide class of endofunctors, which covers pretty much everything you've done, final coalgebras exist. And category, in terms of category theory, you need a property called weak fullbacks. I don't necessarily have to go through that. So let's take the famous Bellman equation. It's a coalgebra. Why is it a coalgebra? Takes an object, right? Some blah, and you do some blah, blah, blah with it, but the blah shows up again on the right-hand side. Whenever you have an equation with a blah on the left-hand side and the blah shows up on the right-hand side, think coalgebra, because this is what produces an infinite data stream. Otherwise, you won't get infinite data streams, right? Because you can keep expanding this, right? Value equals reward plus next state value. That's equal to next reward plus next state value. Keep unrolling. You get infinite data streams. It's a coalgebra. That's why you get infinite data streams, right? So all of this stuff that we've been doing in RHEL all this time is an example of this much more general framework. And I think it's useful for us to understand this framework. So you can define MDPs as coalgebras. I don't need to do this. Guess what? It's been done. Okay, so here's a nice paper. Long-term values in Markov decision processes coalgebraically. Very cool paper, right? By these guys, Fraze, Hansen, and Moss. Moss is a category theorist. So this paper studies Markov decision processes from the categorical perspective of coalgebra and algebra. So why? Because coalgebra blows up the state space, right? So from a state, you do a non-deterministic stochastic transition to any bunch of future states and so on and so forth. That's your search space. Think of a rollout that you do in games like Go or something like that, the coalgebra. But you need to pull back and get a value. That's the algebra. So in some sense, you're combining coalgebra and an algebra, and you should read this paper. Now, here's an interesting research problem for you. This paper is done completely in the MDP setting, no RL here. So there's an obvious question, right? Extend this to the RL setting. Another thesis problem. I'm giving these out to you free, no charge. Okay, so that's all I wanted to say, and I have time check. Three minutes. Oh my goodness. I think I've said pretty much everything I want to say. Non-well-founded set. I gotta tell you this. This is so cool. So Christmas morning, right? 4:30 a.m. on Christmas morning. I am sure all of you were happily sleeping. I'm sure all my neighbors in my lovely little town of Morgan Hill, the Bay Area, were sleeping. I was up at 4:30 in the morning writing out a section of the book on non-well-founded sets. Okay, this is how I am, crazy. So the axiom of well-foundedness states that there cannot be infinite membership chains, but many sets in computer science are not well-founded. Lists, trees, recursion, stacks, they're all infinite, potentially. So you need a new math. And there are lots of examples in AI, like modeling common knowledge, right? We all know things in common, so NLP is effective. We can say a small number of words and convey a lot of information. So it was a breakthrough work of Axel and Mendler on this stuff. But I want to give you a very simple example of a very powerful coalgebra, which is the power set functor. Take a set, any set of real numbers, anything you want, and take its power set. This is the coalgebra. It's called the power set functor. So this is an extremely general coalgebra. You can represent all kinds of crazy stuff, stuff that's not even computable, right? So, but X can be any, well-founded, even non-well-founded set. And the beautiful result is that the set of all, the class of all sets, if you look at that, the initial algebra for that gives you mathematical induction, initial object. The final coalgebra gives you non-well-founded sets. So my big hypothesis is reinforcement learning sits on the right-hand side. Standard machine learning, passive learning sits on the left-hand side. So we have to see two things as different. Standard machine learning doesn't deal with infinite objects. That's always been the province of reinforcement learning, right? Except when generative models came about. All of a sudden, you started dealing with this infinite streams of data, and now we see that these things can be used in all kinds of things. There are simple ways to show that automata form coalgebras. This is done in Brutton's paper and these books, so I don't have to do that. You can do homomorphisms of coalgebras, which is a generalization of MDP homomorphisms and MDP bisimulations, if you know some of that literature. Metric co-induction. Here's a beautiful paper by Dexter Cozen and Nicholas Rosie from Yale saying, hey guys, there is a much simpler way to do stochastic approximation. It's called metric co-induction. Pay attention to this. You should read this paper, but all of the stuff we're doing on convergence theorems for reinforcement learning can be done in a much simpler way. This is my hypothesis as metric co-induction. What does this paper do? They take value iteration in Markov decision processes. The convergence of value iteration in Markov decision processes is used the Banach fixed point theorem. They show that is especially a case of metric co-induction. And once you see that, you can then see that the RL extension is not that more difficult. Of course, it's not trivial, but it can be done. So my hypothesis, Shalom can do a new edition of his book, and it might be much shorter because he can keep saying in every chapter, refer to final coalgebra thing. I'm joking, it's maybe. I'll skip all this, but here's the last thing I'll show, the final coalgebra theorem. The beautiful papers like this says, by the final coalgebra theorem, we actually remember every endofunctor of the category of sets has a final coalgebra, which means fixed points exist for a very large class of problems. And once you understand that, a lot of proofs become much smaller. Right? You can compress the proofs. This is the power of category theory. Because you look at the problems like a bird flying high, you don't get lost in details, and you see the patterns from flying high. Okay, thank you. Let me stop there.
Time for maybe a couple of questions.
Yeah, last. So, like the example of induction, can you give a very basic example of co-induction? And maybe in the context of reinforcement learning, you talk about this Bellman relation. Why is that a co-induction? It wasn't obvious. You can elaborate a bit on that.
That's in the paper, but in the paper I just cited. So imagine. So whenever you construct a solution by successive approximation, what do we do in reinforcement learning? We say we want the optimal value function, but we don't have it. We heard that in the first talk, right? So we successively approximate. So we can do roll-outs, right? So initially I say my optimal value function is just my immediate reward. Well, that's wrong, but that's my first guess. Then we say, oh, let me do Monte Carlo, right? It's 2 steps, 3 steps. I'm basically producing the solution by successive approximations. Keep improving the solution. Whenever you do that, it's co-induction. It's not induction. Mathematically, you can show that. So induction is always the initial object in a category of algebras. Co-induction is the final object in the category of coalgebras. This is the fundamental difference. And RL, I believe, belongs in this co-induction paradigm, right? It's a fundamental different thing than the induction paradigm.
So I have a question, perhaps a slightly provocative one. So usually we try to generalize things or view specific things or procedures in a more general fashion in the hope of understanding them and hence giving some new ideas using that generalized frame. So, right, some kind of payback. Right? Maybe that a general view gives you something more operation different in an algorithmic sense.
Sure.
So, I mean, thinking of back propagation in this general sense is fine. Thinking of reinforcement learning in general sense is fine. But is there any payback yet, or do you anticipate to get any paybacks?
Well,
are there new ways of doing?
Yes, that's my entire argument is that this opens up Pandora's box for new ideas.
Okay.
So for the students, this is your ticket to fame. Or maybe you want to get rich. AI, what is the definition of AI? Get rich quick. This is AI. Okay? You can get rich quick. Well, I don't know the quick part. You have to look category today, but not so quick. But so I totally get your question, right? I agree with you. But to me, how do we start with a new approach? We've tried all this other stuff. There's lots of good work. I'm not going to say this is not good work. We have lots of successes. But as I said, we have a huge energy crisis. We've struggled with value function approximation reinforcement learning for 40 years, keep spinning our wheels there. We need to change something. And I believe that this gives us, different set of tools. I think it's rich. There's already success stories, right? Again, pointing to UMapp as a success story. There are ways of constructing new solutions that come from this that I think we wouldn't understand if we didn't know the math. And I'm a strong believer in the idea that if you start with a secure mathematical foundation, I just quote Vatnik. Vatnik said, "There's nothing more practical than good theory," and that's what I believe, right? So if we wanted to build a true science of deep learning, we have to build on some foundation that is better than what we have. That's my personal.
So when will this lead to an infinite number of papers?
Yeah. I have joked about that to my lab. I said I can imagine myself writing papers into the infinite horizon. I don't know. Look, my dad lived to be 90. That gives me maybe a little less than 30 years. I don't know if I'd be lucky to live so long. CRO lived to be 100. He was 102, I believe. He was writing papers till he was 100. Who knows? The future is uncertain, as we all know. The reason I'm pushing forward with all this and getting these ideas out is because I don't know how long I will live. None of us know. I will take too much time, but I will quote from one of my favorite poets. So Amos is this lovely old New England town, and it has great poets. So Emily Dickinson was a wonderful poet. She lived in Amos all her life. She lived in this lovely house which they have kept, maintained, and you go to Amos, you can go to Emily Dickinson's house. So she wrote beautiful poetry. So here's a poem of hers. Because I made no time for death, death made time for me. The carriage held just the two of us and eternity. So it's a beautiful poem. So